Hi everyone, this is Mrs. J, and today we're going to continue talking about volumes of rotated solids, and we're learning a new method today called the washer method. Alright, I have a quick warm up for you guys to try, so please pause video and hit play when you're ready to check. Alright, go ahead and check your work here. So here's the bounded region, and then you can see it's rotated about the line x equals 5, so it kind of makes this general shape. So here we have horizontal discs. So to find the radius, it's going to be this distance, and we always do the right minus the left, so 5 minus y squared plus 1. And here, since we want that horizontal distance, we want it to say x equals. So that's our radius. So you see I did the integral from -2 to 2. So we integrate with respect to y because the discs are being stacked vertically. And then I have pi r squared, and I just pulled the pi out front. And then the rest is just evaluating your definite integral. All right, so today we're going to be working with rotated solids again. And just like in the last lesson, we're going to be slicing them perpendicular to their axis of rotation, which creates that circular cross section. But this time we're going to be working with solids that are going to have a part in the middle that is missing. So instead of just a disc, we're going to have what's called a washer. So it's a very similar setup. We're still going to define our radius, and we're still doing pi r squared, but here this time we need to define our larger radius, so we can define the area of the entire thing, and then we need to define our smaller radius, so we can subtract away the area of that missing inner circle. And again, the key here is that we do need to make sure our cross sections are perpendicular to our axis of rotation. So here it's rotated about the y-axis, so we can see we have horizontal washers. And if the washers are horizontal, I need to stack them vertically to account for the entire volume. And if I'm stacking vertically, I'm integrating with respect to y. So all of my equations also need to be with respect to y. So you can see it says x equals y cubed, x equals 4y. Now, if I have a horizontal cross section like you see here, a horizontal axis of rotation, my cross sections are vertical, and to cover this entire area, I need to stack them horizontally. So I'd stack them from here to here, from 0 to 3, which means I'm integrating with respect to x, which also means that everything in my integral needs to be with respect to x. And then from there, we just do pi large radius squared minus pi small radius squared, and I'm always going to just factor out the pi and put it out front, and then we integrate over our area. So again, we just need to make sure we're able to define our radius with respect to the correct variable, and then the setup is very similar to our disk method that we learned last lesson. All right, let's try this first one together. So let's start with our bounded region. I have y equals x squared, y equals 1, and x equals 4. So I know that y equals x squared will look something like this, but then I also have x equals 4, and then y equals 1. So I'm going to erase this little part, clean it up a little bit, and I can see this is my bounded area. And here I'm rotating it about the x-axis. So here I have a horizontal axis of rotation, so I know that I'm going to have a vertical cross section. So maybe just for this first one, I'll kind of sketch it out so we can see what these washers look like. So here's the solid, it's rotated 180 degrees. And then here we can see that we'd have that outer ring would look like this, but you can see that I'm actually missing this area in between. So instead of just a solid disc, we have that washer, and then this part right here would represent the area or the volume that we're looking for. So we need to find a way to describe the area of that washer. So we can start by defining our radii. So here again, my large radius is going to be this distance, and you can see that since my radius is vertical, I need to stack it horizontally to cover the entire area, which means I'm integrating with respect to x. So all of my radii, or both of my radii, need to be with respect to x. So again, my large radius is this distance from here to the x-axis. So I'm going to call that capital R for large radius. So that's from my square root equation to 0. And then we can see that our small radius is this distance. So it's from our constant y equals 1 to 0. And I have everything I need for my setup. So again, I'm integrating with respect to x, so from 1 to 4. And then I'm just going to show the full thing out, and then next time I'm going to automatically pull out my constants. But I have pi times my large radius squared minus pi times my small radius squared dx. So that's the general setup of our integral. Then from here on out, I'm always just going to pull the pi out front, and then just do large radius squared, which ends up just being x, and then small radius squared dx. And now I just have to evaluate really quick. So we'll find our antiderivative. So pi times 8 minus 4 minus 1/2 minus 1. So that ends up giving us 9 pi over 2 units cubed. And there you have it. So you can see very similar to the disk method, just accounting for that extra middle area that we need to subtract away. All right, let's try another one together. So let's start with our bounded region. I'll start with my quadratic, so x squared plus 1. So now it looks something kind of like this. And then we have negative x plus 3. So that one will go like this. So I can see that my bounded area is right here. And for this problem, we are rotating it about the x-axis again. Okay, so here, same as the last one, I have a horizontal axis of rotation, so I know that my cross sections need to be vertical. So my large radius would look something like this. That's my large radius, and then my small radius would be this distance. And since I have that vertical cross section to cover this entire area, I know that I need to integrate horizontally or with respect to x. So both of my equations are already with respect to x, so I don't need to rewrite either of them. So if I want to define that large radius, the radii always need to be positive, so I need to do top minus bottom. And notice it's the distance all the way from my linear all the way to my axis of rotation. So it's from negative x plus 3 to 0. And then for my small radius, it's from my quadratic to my axis of rotation, which is just 0. So x squared plus 1 minus 0. Now we're ready to set up our integral. So I'm going to pull the pi out front. We're integrating from negative 2 to 1. And we do large radius squared minus small radius squared. And remember that pi has been kind of factored out from each individual area. And from here, it's just a matter of evaluating. So we do need to multiply out our binomials. So we have x squared minus 6x plus 9 minus x to the 4th plus 2x squared plus 1 dx. We can combine like terms. And now we're ready to find our antiderivative. Okay, almost done. we'll plug in our upper boundary first. So negative 1/5 minus 1/3 minus 3 plus 8. And then we'll plug in our lower boundary. So we get 32/5 plus 8/3 minus 12 minus 16. Then do a little math with your fractions, and we end up with 117 pi over 5. Again, it is important that you're still doing these problems all the way through. You're still maintaining those skills of being able to evaluate and a definite integral by hand. But again, the thing that I really want you guys to focus on for today is the setup. It's super important that we, can at least set up the integrals for these types of problems, especially before we move on to the next lesson where we kind of change up the method that we're using. All right, I have one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and check your work here. So you need to be really careful whenever your bounded area is below your axis of rotation. So we can see we have those vertical cross sections for our radii, and I'm sliding them horizontally, so I'm integrating with respect to x. Now, when you go to define that large radius and that small radius, as I did right here, it's always top minus bottom to make sure it ends up being positive. So here it's actually 0 minus -6, and here is 0 minus your quadratic. So be really careful with that. But from there, we're just doing pi times large radius squared minus small radius squared, and I'm integrating from -2 to 2. Here's all the work for that. All right, let's try another one together. So let's start with our bounded area. So we have these two curves and then rotated about the y-axis. So here's our quadratic. And then here's our linear function, y equals 2x. So it will look like this once it's bounded. And then this time we're rotating it about the y-axis. So you can see since I have a vertical axis of rotation, this time I'm going to have a horizontal cross section. So my the large radius of my washer would look like that, and my small radius would be this distance. And again, here, since I have that horizontal cross section, I need to stack them vertically to cover the entire area. So I'm going to integrate with respect to y this time. That means that my equations also need to be with respect to y, which they're not. So we can fix that really quick. So we can say x equals the square root of y, and it'll just be the positive square root of y because I'm just working with the positive half of this graph. And then we have x equals 1/2 y. So now both of my equations are with respect to y, so I am able to integrate with respect to y. So let's define our radii. So our large radius, again, it's always right minus left to make sure our radii are always positive. It's going to be this function, our quadratic, to the y-axis. So it's square root of y minus 0. And our large radius is the distance from the linear to my y-axis. So 1/2 y minus 0. And now I'm ready to set up my integral. So I'm integrating from 0 to 4. And I've already pulled my constant out front, and then I just have my large radius squared minus our small radius squared. And again, I'm integrating with respect to y this time. So now we just need to evaluate. So y minus 1/4 y squared dy. We can find our antiderivative. And then we just need to plug in 4 and 0, but that just becomes 0. So we have 8 minus 16/3, so 8 pi over 3 units cubed. And there you go. So again, just be aware of, the orientation of your cross section. This one is different. We had that vertical axis of rotation, so we have our horizontal cross sections, which means we're integrating with respect to y, and that also means that our equations need to be with respect to y. All right, let's try another one. You'll notice that I actually have that same bounded area as example 3, but this time I'm rotating it about a different axis. So this one I'm rotating it about the line y equals 4. So here I have a horizontal axis of rotation again. So we need our vertical cross sections. So this would be our large radius, and this would be our small radius. And again, I need to stack those side to side. So here I'm integrating with respect to x again. So I can leave my equations like this. So for my large radius, I always need to make sure it's positive, so I do top minus bottom. So it's the distance from 4 to my quadratic, so 4 minus x squared. And for my small radius, top minus bottom, it's the distance from 4 to 2x, so 4 minus 2x. And I'm integrating from 0 to 2, from left to right. So I have my large radius squared minus our small radius squared dx. Then from here, it's just kind of plugging through, so I need to multiply out my binomials. All of this is dx. Then we have, if we combine like terms, 16x minus 12x squared plus x to the 4th dx. Now we're actually ready to integrate. So 8x squared minus 4x cubed plus 1/5 x to the 5th from 0 to 2. We're almost done. 32 minus 32 plus 32 fifths. So 32 pi over 5 units cubed. So again, it's that same bounded area, but you can see we have a totally different answer because we're rotating it about a different axis of rotation. All right, I have one last problem for you to try. So notice this one you're just setting up. You do not need to evaluate the integral. So go ahead and pause the video and give it a try. All right, go ahead and check your work. So same bounded area, except now I'm rotating it about the line x equals 2. So I have horizontal cross sections. I need to stack them vertically, so I'm integrating with respect to y. So I rewrote my equations with respect to y. And then our large radius is defined by 2 minus our linear, so 2 minus 1/2 y, and our small radius is the distance from x equals 2 in our quadratic, so 2 minus the square root of y. And then you can see we're integrating from 0 to 4, and we have pi r squared minus pi r squared. All right, that is all for today's video. Thank you so much for watching.